Welcome to the next session, my dear students. So in the previous session we have discussed about the alum dosages and the reactions, equations of alum, and also the jar test. Everything we have discussed. Theoretical part we have discussed about the alum. So now in this lecture we are going to learn the alum, how we mix into the water and how we remove the colloidal particles using this alum. What is the actual practical process flow we will learn here. Okay, so that this practical process flow will happen in a clariflocculator. It happens in clariflocculator. So we will learn how to design of clariflocculator. Okay, so this clariflocculator, it consists of three devices. One is flash mixer or rapid mixer. And second one is flocculator or slow mixer. And after this there will be sedimentation tank. So this is the three devices that will be present in the clariflocculator. So let us discuss one by one. So first one is flash mixing. Flash mixing, or we can call it as rapid mixing. See here, it is done in two ways. One is either manually or mechanically. It can be done in two ways, either manually or mechanically. But how we do this rapid mixing is, and what is the intention of doing rapid mixing is to send the coagulant to every corner of the water. That means here the name itself says flash. Flash means we will create turbulence in the water. See, when you add detergent to water in a bucket, then what we will do? You will mix with your hand in many directions, irregular directions, so that it will cause turbulence in the water, so that the detergent will reach every corner of the water of the bucket. So that is the same phenomena here we do in the flash mixing. Flash mixing does not have a pattern, or it may also have a pattern, but the intention here is to send the coagulant to every corner of the water. Okay, to make uniform distribution of the coagulant you have added in water. That is the main motto of flash mixing. Okay, now, so this flash mixing device, as I told you already, it can be done by mechanical stirring based on flash mixers. Okay, or just by simply creating turbulence by changing the direction. So I told you already, we can do this manually by changing the direction of flow, by changing the direction of flow, and also mechanically by using flash mixers. by using flash mixing devices. Okay, so let us see what are the methods which we follow in manual mixing and what are the methods we follow in mechanical mixing. Okay, so first, manual, we use mixing basin. In manual we use mixing basin. Again, mixing basin is of two types: vertical flow mixing basin and horizontal flow mixing basin. So mixing basins, are of two types. One is round and end type, and second one is up and down, over and under type. So this round and end type is also called generally horizontal flow type. Okay, this is also called horizontal flow type. Okay, horizontal flow type. This is vertical flow type. Vertical flow type. The mixing basin will be like this. So this is the inlet, and we will be having a baffle walls kind of arrangement. We will be having a baffle kind of walls arrangement. So here, if the water enters here, so the water has to travel like this. This is outlet. So because the water is keep on changing its direction, so by changing its direction continuously, we are creating turbulence in the water. So this is the mechanism which we use to introduce the coagulant into the water, and we can disperse this coagulant using this kind of technique. See, if you look at this from the top, that means if you look this as a plan, if you see this like a plan, okay, so if you are looking this plan, then that plan indicates the horizontal flow type. Okay, plan indicates horizontal flow type. See, that means when you are looking the plan like this, the water is entering from the inlet like this, it is moving and it is moving like this. This is the movement of the water. Right? So that means horizontal, the flow is horizontal and the baffle arrangement is in horizontal plane. This is the movement of the water. So that is round and end type of manual flash mixer, round and end type. If the same thing, if you are looking like a vertical plane, so this is the entry of the water, and now the water is traveling like this. So up and down like this, over and under, that is called this. That means if you are looking it like in vertical plane, then it indicates, that means elevation indicates vertical flow. Okay, elevation indicates what? Elevation. If you look this as elevation, then it indicates vertical flow type. Okay, so these are the mixing basins, but The mixing basins are obsolete. We are not using them anymore. So these are not in use. Okay, we are now depending completely on mechanical mixing devices only. Mechanical mixing devices only. So let us see what are the mechanical mixers now. Mechanical mixing devices. Mechanical mixing devices. There are two types of mechanical mixing devices. Again, here also vertical shaft and horizontal shaft. Vertical shaft and horizontal shaft. Vertical shaft and horizontal shaft. That means when there is a vertical shaft, then it looks like this. This is the inlet and this is the outlet. The inlet and outlet, and this is a shaft, vertical shaft. It will be having two paddles. It will be having two paddles. So it will be having two paddles like this. So this is inlet and this is outlet. So here the shaft is in vertical direction, so that is why it is called vertical shaft. This is called vertical shaft. This is effective in comparison with horizontal shaft. Okay, this is more effective than horizontal shaft, but costly. Okay, whereas if you look at the horizontal shaft, this is the inlet, so the shaft will be in this direction. The shaft will be in horizontal plane. Earlier the shaft is in vertical plane, now the shaft is in horizontal plane. This is horizontal shaft mixing device. This is inlet and this is outlet. Okay, these are the vertical shaft mixing device, flash mixing device, and horizontal shaft flash mixing device. Horizontal shaft flash mixing device. And now let us see the parameters, the design parameters of these mixing devices, flash mixing devices. How the mixing happens, mechanism we will discuss now in a clear manner. And what is the speed of rotation of these paddles, what is the duration, and how we decide the speed, and what happens if you increase and reduce the speed of the paddles. All these things we will understand now. The complete mechanism of the flash mixing device. Okay, in these mixers, coagulant and raw water is thoroughly mixed for neutralizing the negatively charged particles. So in these mixers, what we do? We mix the water thoroughly. Okay, so that all the coagulant will reach to the negatively charged colloidal particles and neutralize them. And the intensity of mixing depends on a parameter called temporal mean velocity gradient. So the intensity of flash mixing is governed by a parameter called temporal mean velocity gradient. Temporal mean velocity gradient. Okay, this is the parameter on which the flash mixing will depend. So for ensuring a uniform distribution of a coagulant, orthokinetic condition prevails. See, here our intention is to uniformly distribute the coagulant to everywhere. So that means, so there are two conditions. One is perikinetic and orthokinetic. Here we ensure orthokinetic condition in order to have a coagulant uniform distribution. Okay, so for uniform distribution, of coagulant, we maintain orthokinetic condition. What is this orthokinetic condition? So this means, orthokinetic condition means the mixing is due to collisions by bulk fluid motion. Okay, the collisions, so the mixing is orthokinetic condition means the mixing is due to collisions caused by bulk fluid motion. The mixing is due to collisions caused by bulk fluid motion due to stirring, such as stirring. This is called orthokinetic condition. Orthokinetic condition means when you are mixing any item or any compound by making bulk fluid motion. So if you are mixing it or stirring it, what happens? You are moving the fluid. And causing more collisions inside the medium or water. So that is nothing but orthokinetic condition. So here we maintain which condition? For flash mixing, we maintain orthokinetic condition. In order to have uniform distribution of coagulant. So here in orthokinetic condition, the velocity of fluid varies spatially and temporally. Here in orthokinetic condition, velocity of fluid varies spatially It is point to point, point to point, and temporally, and it varies temporally, that is time to time, time to time. So here in orthokinetic condition, what happens? So the fluid velocity varies spatially as well as temporally. Now that is why at any instant of time, the ratio of relative velocity between two particles, okay, so at any instant of time, the ratio of relative velocity between two particles situated by a particular distance x, situated at a particular distance x to its distance is nothing but temporal mean velocity gradient. Why we are taking temporal mean velocity gradient? Because here we are maintaining orthokinetic condition, and the intensity of this mixing dependent on temporal mean velocity gradient. Let us see what is temporal mean velocity gradient. The name itself says, very easily we can understand temporal mean velocity gradient. It is a very important parameter for the clarifocallator. Either it may be flash mixing or it may be slow mixing. Both are governed by this temporal mean velocity gradient only. What is the intensity of mixing, whether you are making it with greater intensity or making it lighter, smaller intensity, all those things we can vary by just changing a parameter called temporal mean velocity gradient. Let us see what is temporal mean velocity gradient. See, for example, if you look at a mixing device, I have told you already, this is how we look at a mixing device. Okay. Now there is I am taking a horizontal mixing device. So this mixing device rotates like this. It induces velocity in the water, right? So I will take some plane like this. I will take an axis like this, and I have taken another axis like this. On this axis 1, 1, and on this axis 2, 2. So the velocity at different points on the axis varies. The velocity of particle at different locations on this axis will vary. So if I take a mean velocity of all the values present on this axis, that is called mean velocity of 1, 1 axis. Similarly, I will take a mean velocity of 2, 2 axis. So if you look this here, so I have taken 1, 1 axis, the mean velocity I have taken it as V1. I have taken the mean velocity as V1. This is V1. Similarly, I have taken another axis where the mean velocity is V2, and they both are separated by a distance of x. So again, this velocity varies with the time, because I told you orthokinetic condition means velocity varies time to time, place to place, spatially and temporally. So that is why at a particular instant of time, okay, at an instant of time, these are the mean velocities. At an instant of time, these are the mean velocities. So temporal, at an instant of time means temporal. Mean means you are taking a mean of velocities of a particular axis. Temporal mean temporal mean velocity gradient. Velocity gradient means v2 minus v1 by x. Velocity gradient, this is nothing but velocity gradient v2 minus v1 by x. So at a particular time, at an instant of time, the gradient of mean velocity, the gradient of mean velocity is nothing but temporal mean velocity gradient. We represent it with z. Temporal mean velocity gradient. So this is v2 minus v1 by x. What are the units of it? So velocity unit is meters per second and distance unit is meter. So second inverse is the unit of the temporal mean velocity gradient. Second inverse is the unit of temporal mean velocity gradient. And here g, we are looking this g from the velocity point of view. If you look the g from the shaft point of view, that means how you are making this shaft to rotate by giving some mechanical energy from power energy. So we can also control this g from the power supplied to the shaft. You are looking from the output point of view. That means when you give power to the shaft will rotate. If shaft rotates, it will induce velocity in the water. So if you are calculating this g from the velocity of the water, that is from the output point of view. Similarly, you can find this g from the input point of view. That means the power supplied to the shaft. From the power supplied to the shaft, there is a formula to find g from the power supplied to the shaft, that z is equal to square root of p by mu into volume. P by mu into volume. So P is the power supplied in watts. Power supplied in watts. Power supplied in watts. And V is the volume of mixing basin in meter cube. Volume of mixing basin in meter cube. Volume of mixing basin in meter cube. Mu is the dynamic viscosity of the fluid, that is water. Dynamic viscosity of water or the fluid in the mixing basin. Dynamic viscosity. Here this is an empirical formula. We need to remember the units. Units are very, very important. Volume of the mixing basin should be taken in meter cube and dynamic viscosity should be taken in Newton second per meter square. Newton second per meter square. So this formula is very, very important for gate. This formula is very, very important for gate. So the G you can either find from velocity gradient or you can find from the power supplied to the shaft. Power supplied to the shaft. So now to ensure the rapid mixing, what should be the Z value? To ensure rapid mixing, G value should be kept in between 700 to 1000 second inverse. To ensure rapid mixing, so we need to keep the value of Z in between 700 to 1000 second inverse. 700 to 1000 second inverse. This is the value we need to keep to ensure rapid mixing. And also we can control this by supplying power also. So to ensure the rapid mixing, the power should be 123, okay, 123 watt per meter cube per hour. So the power should be 123 watt per meter cube per hour. So this also ensures rapid mixing from the power point of view. From the power perspective, it is 123. From the velocity gradient perspective, it is 700 to 1000 second inverse. So what are the design parameters? Now the design parameters of the flash mixing device. Generally flash mixing device will have a impeller, paddles. Okay, so what is the impeller diameter, how the velocity is being induced in the for inducing the sufficient velocity into the water, what should be the velocity of the paddle, how to calculate it, what is the drag on the water, all these things we will see in the design parameters. Okay, so design parameters of flash mixing device. Design parameters of flash mixing device. Design parameters. See here, depth to width ratio of the tank, depth to width ratio, depth to width of tank, that is H is to B. So H is to B varies from, for square tank H is to B, for square tanks, for square tanks, and for H is to D for circular tanks. For circular tanks, it varies from 1:1 to 3:1, 1:1 to 3:1. So varies from 1:1 to 3:1. So this is height width or diameter. So this is the depth to width ratio. Impeller diameter to tank diameter. If the tank is circular, then impeller dia by tank diameter. Tank diameter should be equal to 0.2 to 0.4, 0.2 to 0.4 meter. Depth of the tank varies from 1 meter to 1.5 meter. Depth of tank varies from 1 meter to 1.5 meter. 1 meter to 1.5 meter. So volume of the mixing basin, volume of mixing basin Q into dt. If you know the inflow into the mixing basin, and if you know the detention time dt, then you can find the volume of the mixing basin. Generally detention time is kept as, for flash mixing, detention time varies between 30 to 60 seconds. It varies between 30 to 60 seconds. It varies in between 30 to 60 seconds. Surface area of the mixing basin, surface area of mixing basin is equal to volume by depth. So volume by depth, then you will get the surface area of the mixing basin. And the n varies. N value means rotations per minute, RPM. rotations per minute varies from 100 to 120 rpm. N rotations, number of rotations N varies from 100 to 120 rpm. N varies from 100 to 120 rpm. 100 to 120 rpm. Now the speed of the value of this n, okay, the speed of the shaft, it depends on the speed of the shaft. The speed of the shaft should be such that tangential velocity should be greater than 3 meter per second is imparted at the tip of the blade. What is this? Let us see. The velocity of shaft should be such that it should induce a tangential velocity of Vt should not be less than 3 meter per second at the tip of the paddle, at the tip of the blade or paddle, whatever it may be, at the tip of the blade. So what is that? Let us see. So if this is shaft, these are the blades. So this is the tangential velocity. This tangential velocity should be greater than 3 meters per second. Should be greater than 3 meters per second. So you have to induce a RPM such that it should induce a tangential velocity of 3 meters per second at least. And let us take, this is the R value to the center of the plate. Let us take, this is R, small r. So from here to the outer, let us take this as R dash. Let us take this as R dash. And let the plate paddle velocity is Vp. The velocity of paddle at the center, that is Vp. Okay. So Vt is equal to this Vt is equal to omega, that means angular velocity, into R dash. Omega into R dash, where omega is equal to 2 pi n by 60, where n is revolutions or rotations per minute. Rotations per minute is n. R dash is equal to R dash. Here R dash is equal to R plus B by 2, where B is width of the blade or paddle. Width of blade. So by this we can find the Vt, tangential velocity, which is equal to omega R1. Omega is 2 pi n by 60. N is the rotations per minute of the shaft, and r is the center distance of the center to center distance of the shaft center and the blade center. B is the width of the blade. This is B. This is B. Okay. So this is nothing but r dash. So from where we can find Vt, and we can compare whether sufficient Vt is being generated or not. Okay. So next is, we have calculated G from velocity gradient from the outlet point of view, and we have calculated G from power point of view. So similarly, we can also calculate this G from the drag of the blade, drag on water from the, so the blade will drag the water, right? So to rotate the water, the blade should drag the water. So then the blade will be offering drag force onto the water. Similarly, the reaction drag force will come onto the blade of the plate, blade of the shaft. Okay. So let us calculate what is the drag force that will come onto the blade, or that is being induced into the water. Let us see that. See in the figure which I have drawn now, from the figure, so I will draw the figure again. Okay, so here this paddle is rotating like this. It is rotating like this. That means it is inducing some velocity in the water. It is inducing some velocity in the water. Let the velocity in the water is Vw. Let the velocity in the water is Vw. So Vw is velocity. Vw is velocity of water. Vw is velocity of water, and Vt is tangential velocity. Vt tangential velocity. Vt is tangential velocity, and Vp is velocity of a paddle or velocity of blade. Vp is velocity of paddle or blade. Okay, next Vr is the relative velocity. Vr is relative velocity. Vr is relative velocity. What is relative velocity? Vp, so that is the velocity of paddle, and Vw is the velocity induced in water. The relative velocity is equal to Vp minus Vw. The relative velocity is equal to Vp minus Vw, and mu is the dynamic viscosity, and V is the volume of the tank. Volume of tank, and mu is dynamic viscosity. Mu is dynamic viscosity. So n is the number of paddles. See, sometimes we may have a series of paddles. So this is one paddle. At some spacing there will be another series of paddles. See, for example, if you look at a three-dimensional figure like this, this is one paddle. Somewhere there will be another paddle. So this is a tank. This is a tank. In this there will be series of paddles rotating. Okay, so sometimes you may have series of paddles. So when there are series of paddles, there will be number of paddles. See, for each shaft there will be two paddles. 6 paddles are there here. So similarly there will be number of paddles depending upon the different kinds of shafts, series of shafts. Okay, so n is the number of paddles. N is number of paddles. So here the drag force, we will define first the power using the drag force. What is power? Power is nothing but force into velocity. Force into velocity, that means force here is drag force. Drag force. So here the paddle is dragging the water. The paddle is dragging the water with some drag force. So here because of this drag force, velocity is generating in water, and that generator velocity is VW, but along with the paddle is also moving. Paddle is also moving along with water. It is pushing water and it is moving back of the water. So the system is rotating with a relative velocity. If you look at the whole system, paddle is also moving in the direction of water. Water is ahead of paddle. So both are moving like a system. So we need to take the relative velocity of the system, that is VR. Okay. So power is equal to FD into VR. So now what is FD? Drag force. What is drag force? I think you might have learned the formula of drag force in your fluid mechanics. So here the drag force is nothing but 1/2 CD rho W, 1/2 CD rho W AP into VR square. 1/2 CD rho W AP into VR square for one paddle. For one paddle. So when there are n number of paddles, then you need to multiply it with n. You need to multiply it with n. 1/2 CD rho W AP VR square into n for n number of paddles. For n number of paddles. Okay, for n number of paddles. Now this is power term. This is force, drag force term. Now we know what is power. So this drag force into velocity. And we also know the G formula in terms of power. P by mu into volume of the tank. So G is equal to, P is nothing but what? FD into VR by mu into V. So FD, what is FD? FD is 1/2 CD rho W AP VR square, and this is FD multiplied with VR by mu into volume of the tank. Mu into volume of the tank, that is, this is equal to square root of 1/2 CD rho W AP and VR cube by mu into volume of the tank. So this is the formula of temporal mean velocity gradient. Temporal mean velocity gradient when we want to find using drag force. When you want to find using drag force. So this is all about flash mixing. In the next session we are going to discuss slow mixing. Okay, we are going to discuss slow mixing followed by sedimentation. Okay, thank you so much.